So given that at least everybody in the room is on par with what neuromorphic computing is, it's fair to say that a lot of neuromorphic computing research looks at how to enhance systems that are portable, that is, at the edge. But I like making life somewhat tough on myself, and I like to ask, what are the most expensive workloads out there? Because it should make a fair bit of sense to optimize those as well, right? Um, and so let's target them. And that is a big part of what my lab does with respect to neuromorphic language models. And for the next 45 minutes or an hour or so, I will run you through our wins and our failures with respect to these neuromorphic LLMs. Before I go into AI and all the fancy stuff, I will show you the cutest photo you will ever see in any academic presentation. More precisely, this is 30 years ago. This was me and my sister. My sister's Tash. So I was too young for this 2XL robot. There were many major AI safety concerns, a lot of moving parts, very dangerous stuff, very dangerous stuff. High risk, high risk. Tash did not care. My sister didn't care about AI safety. So she very irresponsibly gave this robot to her 3-year-old brother. Sure, maybe this was the life-defining moment where I'd go on a trajectory of working on artificial intelligence and all of that. I'm not here to tell you about my history, though. This is a lesson about gratitude. I was so excited. I took the robot, I ran off with it, and my sister calls out, "It doesn't cost you anything to say thank you." I'm a very patient person, and it took about 30 years to validate that, yes, it indeed does cost you a thing or two to say thank you. So I don't know, maybe manners doesn't get you anywhere, but what are some possible routes to making this cheaper? One avenue might be
You could stop
neural
computing.
networks,
Thank you.
perhaps. So I want to distill this down to what I'll call the 3 S's. So the first is that biological neurons interact via these single bit spikes. So let's take this cartoon depiction of a neuron. And if I take an electrode and I stick it, if I was to stick it into the neuron body, right, then I'd see a bunch of voltage fluctuations and whatnot. But if the moment I move that, say 1 to 2 millimeters away from that body, down the axon, all of that noise is attenuated, right? And I only see signals if that neuron is sufficiently excited in the form of this, say, approximately 100 millivolt perturbation of an action potential. So that's the only time the neuron is really communicating with other neurons. Now, in population studies of these guys, the computational neuroscientists tend to abstract away the exact trajectories of that voltage. They'll like to say that, look, all we care about is whether or not a spike happened. And the amplitude, the pulse width, et cetera, are pretty similar. So let's just treat it as a 1 or a 0. And computationally, this makes sense because the dominant cost of a lot of neural nets is memory access, right? They're heavily IO-bound or memory-bound processes. And so if I'm taking a numerical 0 as the output of a neuron and I have to broadcast that out to 10,000 parameters, 10,000 weights, well, 0 times any of those weights is just 0. Sounds like an operation that you can skip, right? So the vibe is there. There's some potential computational benefit from this. Then we could push it a little further and account for sparsity, right? Biological neurons are ridiculously slow compared to your gigahertz microprocessors. In practice, you're on the order of firing at hertz and even slower sometimes. So most activations in that picture are going to be 0 at any given time. Now, I could read this list out to you. I could say 0, 0, 0, blah, 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 7, 0, 0, blah, 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 5. That was a massive waste of my breath and a 3-second waste of your time. It makes a lot more sense for me to just say, I've got a 7 at position 10 and a 5 at position 20, right? That is, you're only adding to your memory usage or adding to your cache every time you have a non-zero element. So I want to, go ahead.
And I just to clarify, so is it accepted that it's a single bit spikes? But then they also talk about rates of spiking rates.
Yeah. So the question there was, is it commonly accepted that there are single bit spikes? Because people also talk about rates. And in the picture of rates, you have multiple spikes and you're able to aggregate them together. And you could potentially interpret that as a multi-bit type of spike. So this has a lot of nuance to it. I would say that, yeah, you can absolutely generalize to multi-bit spikes. And rates are one way to kind of illustrate that in your mind. Another way might be that Your spike arrives at your dendritic tree, and then by the time it arrives at the soma, it's perhaps attenuated a little bit, and that could give it some sort of amplitude. So with respect to the first S, there is no need to have a single bit spike. Intel kind of, I don't want to say realize that, but a lot of neuromorphic hardware that's out there has relaxed that single bit constraint as well. Why? Because binary activations suck in deep learning. So from a practical functional perspective, that is no longer it is no longer a constraint. What really matters here is sparsity. The benefit you get from 1 times a number, sure, you'll get some sort of computational efficiency out of that, but the efficiency you win is significantly less than what you get from skipping memory accesses. So stay logical, stay work. You don't over-optimize for the wrong thing. And I will bring back that single bit assumption and where it hurt us in a moment as well. Yeah. But I do want to distinguish these two. I mean, both benefits come from some form of sparsity. The first one lets us execute less operations, and the second point is about using less memory. And the final one, I'm not going to look at event-driven processing, or I've kind of meshed it so that it fits the 3 S's mantra: static suppression, or 4 S's. But the idea is simple. The sensory periphery only processes information when there is something new to process. You're looking at my slides, you're looking at me waving my hands around, whatever. If I asked you how many exit signs are there in this room, you probably couldn't tell me, even though the answer is right in front of you, because you haven't been paying attention to it. So your brain knows when to suppress information. Maybe if there was a fire, then you'd start looking for the exit signs. But with that being said, we've kind of taken some of these principles and what's one way to really leverage these into deep learning? Maybe it makes sense to abstract away a lot of the low-level dynamical systems and into a simplistic recurrent neuron that changes over time that transmits these 1-0 spikes, right? And that is, a leaky integrate and fire neuron may be one possible route here. I won't derive it from scratch, but the spirit of it is this. Say you've got a neuron and you have a series of input current injections also as spikes. Now, if that neuron is sufficiently excited, only then does it transmit its own spike to all of its downstream connected neurons. Only then does it execute memory accesses and whatnot. If I pop the hood a little bit and said, on the top plot, I've got input current, and on the bottom plot, I've got the membrane potential or the hidden state of this neuron. That is, if I was to probe the difference of voltage between the intracellular and extracellular medium, then I'll see a jump up voltage, which kind of exponentially relaxes back to some steady state value. So you've got this leakage mechanism just integrated by, charge decay. And then when you have a train of spikes, then this membrane potential starts accumulating on top of itself. That's your integrate. So you've got leak, you've got integrate. And in this abstraction, we've set an arbitrary threshold to 1. All these values are normalized. And then you get a spike, right? So you've got leaky, integrate, and fire. Quite a simple first-order dynamical system. And of course, there's this reset mechanism that you may or may not want to add every time you reach a spike, or every time you reach a threshold. Then you reset your membrane potential as well if you wish. Good. So we took that, snowballed it into SNN-Torch. This was my COVID baby. I think I started working on this in 2019, 2020. It's an open source Python library. It's a thin abstraction layer on top of PyTorch that effectively makes it mind-numbingly easy to train spiking neural nets. So it enables a few exotic real-time online learning rules. You'll be able to learn a little bit more if you're still around at 4 p.m. and want to hear me talk a little bit more in the EMBS seminar. It integrates very cleanly with PyTorch, and I use the word seamless before ChatGPT was a thing. This predates ChatGPT. It's had a couple of downloads, and it's also compatible with neuromorphic hardware. A couple places are using it as well. In particular, I think the NASA's application has been quite cool. If you point a camera up into space, there's a hell of a lot of nothing in space. So it makes sense to suppress a lot of that information, right? And if you do want to go super deep into it all, there's a rather extensive set of tutorials. I kind of think of it as like a dynamic textbook, all in the form of Colab notebooks. So you can interact with the code and get quite low level with it all. So with all that being said, it's not surprising that language models are the place where we are exploring the utility of neuromorphic computing. There is, of course, the energy efficiency angle, but I don't know, some view that language is perhaps is a key word there, the foundational unit of logic and reasoning. There have been papers in the past couple of years that vehemently go against that thought. And while that is a separate debate for now, it does make a lot of sense to use brain-inspired concepts to do brain-like reasoning. So I'm going to give you a very, very fun example on, this is very fun, of how modern transformers work in a very simplistic way. Take this sentence, right? Shrek saw Taylor with binoculars, right? Think about that for a moment. My question to you is, who has the binoculars? Is it Shrek? Is it Taylor? Right? Now, linguistically speaking, it's ambiguous. It could be Shrek, it could be Taylor. But given that we're humans with some sort of deductive of capabilities, we can probably infer that Shrek saw somebody else, and therefore Shrek has the binoculars, right? Now, each of these words, more precisely tokens, sub-pieces of words, gets represented as a vector and gets passed through many, many series of operations. Eventually, somewhere in the model, there's going to be the construction of what's called a self-attention matrix. And that self-attention matrix, all that's trying to do is find the relationship or the correlation between a given word or token and every other word or token. In the case of self-attention, you might see that the number representing the relationship between Shrek and binoculars lights up very strongly, right? So self-attention is perfect memory in a way. It's storing every single thing that it's ever seen up to a particular limit, and it's able to find that relationship. So you might be able to appreciate, if I extend this sequence length, if I throw a PDF file, I'm going to be adding something along the x-axis, I'll be adding something along the y-axis, yeah? So this could get quite expensive, right? That is, in a naive implementation, memory is going to grow quadratically with increasing sequence length. I think it's safe to say that we can appreciate that your brains do not undergo neurogenesis with every additional word that I say. You're just extracting the semantic ideas of what I'm getting at and making your own conclusions rather than memorizing every single syllable that I've drilled on about in the past 20 minutes. So what if I was to replace this with a recurrent neuron or a spiking neuron? Well, there's a bit of a problem here because by the time you arrive at the final token, binoculars or word, there is this risk that all information about something that happened a while ago, Shrek, has vanished, right? Or potentially been superseded by Taylor. If I bring back this Leaky integrator example, perhaps this first current spike represents Shrek, and by the time you reach the end of that sequence, all of that glorious information about Shrek has faded, right? And so what's the issue here, right? So attention, in a way, it has too much information, but it works really damn well. Spiking neural nets and more generally recurrent neural nets, they don't have enough information, but goddamn, they are cheap. Wouldn't it be nice to be able to bridge that gap? So the first effort that was really put into bridging that gap was we started in 2023. We developed SpikeGPT. It was the first spiking neural net trained via backpropagation and the first to perform language generation. It was, the catchphrase was that we were able to achieve 30x less operations thanks to sparsity compared to a standard transformer. Now, of course, there's always a catch, right? The model that we trained was something like 216 million parameters. And I hope we are somewhat aware that modern large language models are erring on the side of trillions of parameters. So this guy is 10,000x smaller than anything that you're relying on to definitely not do your homework or assignments or research papers or grant writing. With all that being said, why, other than that issue, why aren't people using it, right? Scaling hurts. I'm not here to sell you on a pipe dream. Scaling really hurt. We tested out how this model behaved at the 1 billion parameter regime, a mere 5x above what we reported, the 216 million parameter model. And the performance improvement was, quite frankly, negligible. It did not follow the scaling projections that we were seeing from modern non-spiking deep learning. What does that mean? Did that mean that my past 10 years of research on SNNs has been a waste of my time? Well, hopefully not. I mean, maybe not in the way that we were approaching it with SpikeGPT, but we did take a lot of lessons away from that. We did theorize as to why scaling hurts so much. One thought is that training SNNs is hard. They're very sequential, true. They're non-differentiable because spikes, they rely on a hard threshold. But that's somewhat been addressed, I think. People would just apply gradient approximations to train spiking neural nets, and we know that this generalizes at larger scales because we've seen quantization-aware training, we've seen ternary parameters being trained. All of them use gradient approximations. Hell, even the optimizers that you might use in training your neural nets don't rely explicitly on updating your weights using the raw gradients that you've calculated. It's more of a momentum of gradients, or depending on what you do. So that the approximations models are very tolerant to approximations of gradients. So really, what it must have been was compression. It's the binarization of gradients that was really killing us here. That is what led Intel to start working on multi-bit spikes, to focus more on sparsity rather than these compressed numerical formats. So yeah, go ahead. The number of parameters. No, not in terms of data yet. So just purely parameters at this point. Yeah. So what did that lead us to? What's some about this perhaps failure did teach us a thing or two. That led us to this quirky model, the matrix multiply free language model. Look, it's a model that is recurrent, but is linear through time. So you might have heard of state space models at some point. And so there are a lot of nice properties in having linearity through time. You project nonlinearities through space, but if you have linearity through time, then you can effectively introduce a closed form solution that lets you accelerate training runs on GPUs by representing something that would be sequential, trying to find t equals 1, then t equals 2, then t equals 3. All that can somewhat be calculated simultaneously and represented as parallelizable convolutions or parallel or associative scans. So state space models that are very parallelizable can also represent spiking neurons by just acknowledging the fact that a Leaky integrator is, for the most part, just this exponential curve, right? You can calculate all points along that exponential kind of in one hit. So the structure of state space models in this MatMul-free model is very similar to what a spiking neural net would look like. The question might be, how is it MatMul-free? Because truth be told, if I saw this paper title and something released, I'd be like, no, that's bullshit. I do not buy this. So in transformers, there are two primary places where you might see vector matrix or matrix arithmetic. You've got self-attention and dense operations. So we turned single bit activations into ternary. Sorry, from SpikeGPT, we had single bit activations. In the MatMul-free model, we relied on the same principles to train low precision parameters, but instead with ternary weights. It turns out that ternary parameters are far more tolerant compared to single bit activations. Then in self-attention, remember, your memory expands as your sequence length grows. Everything gets memorized up to the limit of your context window, but our goal here is to sidestep that. So if you have a finite amount of memory across your many experiences, across your tokens, across your sequence length, then something's got to give. And that is the case with RNNs. That's why people moved from RNNs to self-attention. So your model has to forget something. So we pay homage to Schmid-Huber and LSTMs here and borrow the notion of learning to forget. We just make sure it's linear through time. Everything in that setup, in the learning to forget paradigm with state space models, are all expressed with element-wise products. So again, sidestep any memory bottleneck that comes from from accessing matrices, and effectively MatMul disappears from this. Now, I'm not going to go into too much more detail here because there is more interesting stuff to talk about, but unsurprisingly, GPUs aren't the most optimal hardware for these rather sequential workloads at inference time. And given the very consistent profile of state space models with spiking neural nets, it maps really cleanly onto neuromorphic, quote unquote, brain-inspired hardware, things that have been things that are intended to accelerate spiking neural nets. So we custom mapped this to Intel's Leaky 2 chip, a neuromorphic processor. And quite recently, we were able to hit 2 watts at human readable throughput and effectively meeting the same benchmarks on short context benchmarks when compared to Transformer++. I'll show you that in a moment. So this is a high-level block diagram, which I won't spend too much time on. Every block has a sequence of token mixes, channel mixes, if that means anything to you. If not, don't worry too much about that. And what you're seeing here is Intel's neuromorphic processor Leaky 2, or a system of 128 of them. each dense operator kind of maps onto a certain number of cores, somewhat color-coded. Your mental model on a multi-chip system might be something like this. And this is very abstract, but bear with me. Layer 1 perhaps goes on to chip 1. Actually, let me see if I can show a laser point. Beautiful. So layer 1, or block 1 might go onto chip 1. Layer 2 goes onto chip 2. And so your data flow looks something like that to go from input to output. And in the single-digit billion parameter models that we tend to train, they might have 24 to 32 blocks or layers. So without further optimization, that requires 24 to 32 chips if you're not going to compress multiple blocks onto single chips. So that's 32 chips that are yapping to each other effectively. One catch is that language models tend to operate in two different modes: autoregression or decoding and prefill. Can I get a show of hands? Who knows the difference between these two? Beautiful. I got slides for this. I came prepared. So what is prefill? Let's take this screen capture of ChatGPT, who would win in a drunken brawl at Carl's between a banana slug or King Triton. There's no UC camaraderie. And I'm pausing right there at the generation of the first word. Right? That's prefill. I just showed you prefill. More concretely, given an arbitrary sequence of length n, right, predict the next token. And indeed, it did predict the next token. It was at, right? Given that there are many tokens available to you, and then you hit enter, kind of pushing all of that into your pipeline or across your many cores, all in one hit. So prefill is a highly parallelizable process. In fact, for a long enough sequence length or large enough batch size, it's a compute-bound process, which is kind of rare nowadays in deep learning. So the point is that for a sufficiently long sequence, all of your chips are active. They're all stacked with perhaps your entire PDF file, right? Let's consider the second operating mode, decode. Once you have generated your first new token, that output token goes back to the input of your model and has to flow through your layers again. But the only thing that changes is that one new token. You've already calculated your previous sequence. You've got attention scores for that long input sequence, right? So you only need to calculate the newest token given one previously new token, right? So now you're watching the decode phase, right? So all you have to do is run a set of calculations to account for the newest token word by word. So at this stage, parallelism isn't possible over your sequence because I can't start my next word until my previous word has kind of flown all the way through my entire system from start to finish. So not a very parallelizable process, and autoregression ends up being memory bound. And in practical modern systems, LLM servers tend to execute prefill on their highly jacked up H200s fancy GPUs that have a lot of flops, and they delegate decode, which is memory bound, and they don't require as much compute to, I don't know, the slightly lower performance GPUs, and that is all in the name of cheapening the cost of serving people. So A6000s and one. So more concretely, given one new input token, predict the next token. Great. So my question is, in a single tenant, single user, single batch case, how many chips are active during decode? The answer is here. Right? One out of many. Only one layer is really processing before it generates a series of activations to transmit to your next chip. Now, in a 1.3 billion parameter model, this, in our case at least, is approximately 4% of the overall system, right? Now, my initial and very naive thought was that given that most of your chips are off, this is a highly sparse system, and neuromorphic hardware loves sparsity, so these are a natural fit. I'm sure I would be able to convince many of you that this indeed is a natural fit. But this was honestly the wrong framing to kind of view this problem as, because static power and leakage power ends up being far greater than dynamic power, right? All of your parameters on these so-called off chips are still being stored. And in these cases, they're stored in SRAM, right? That's leaking energy. What that means is that in such a system, I could crank up the activation sparsity. I could use all the spikes. I could get all the zeros in my active layer as I want. And really, I'm only going to help 4% of my system, and that ends up being quite wasteful. It's kind of the wrong engineering effort. Yeah. I'm targeting the wrong problem there. So we should really be focusing on the biggest strain on the system, at least during decode and auto regression. That is static power. Any thoughts on how we might reduce static power? I know Gert knows, of course he knows. We're not re-engineering the SRAM. We could go to NVMe and whatnot too, but let me give you a solution that I'm more comfortable with at the software abstraction, right? Well, what determines static power? The amount of SRAM here that you're using. What determines the amount of SRAM that you're using? The size of your model, perhaps, right? How can you compress the size of your model kind of in a way that neuromorphic hardware is a fan of? Weight sparsity, perhaps. You can reduce the number of chips used by reducing the amount of on weights, and you can compress the total number of parameters that are actively engaged in your model at any given time, right? Somewhat abstractly, I could say that instead of having block 1 on chip 1, block 2 on chip 2, if half of my weights are 0, then perhaps I could compress layer 1 and layer 2 onto one single chip. Then if I'm halving the number of chips in my overall system, then bam, that's halving the amount of static power that I need to burn. Yeah. So these are the main takeaways that I want you to at least have concrete in your mind. 1, activation sparsity isn't useless. It does help prefill and multi-tenant workloads, at least in this right-hand case, because everything is active there. Weight sparsity helps with decoding and single-tenant workloads in this left-hand case here. So you got to typically choose one or the other. I mean, you can co-optimize to some extent, but they're both going to give you different benefits. And the neuromorphic community, I don't think that we kind of had a common consensus on this, because there's very few groups that are really working on large-scale neuromorphic systems that can leverage sparsity like this. That's all well and good. We are still relying on GPUs and floating point, half precision, full precision arithmetic to train these guys, but if we want to test it on something that actually milks ternary operations and can optimize for sequential workloads, then we need to look at custom hardware, and that is where Leaky 2 benchmarking comes in. So let me show you the results that matter. On the x-axis, we have joules per token. How much energy does it take to generate one new word or token? Lower is better, right? This is where we want to sit. On the y-axis, we have throughput per watt. How many tokens can I generate in 1 second given 1 watt of power? In that case, higher is better. So the sweet spot is really something up here. And in green, we've got the Transformer++ model, which is kind of a good representative of most open source LLMs that are out there, Llama, Qwen, etc. The size of the models represents a 1.3 billion parameter model and a 2.7 billion parameter model. And if I show you where MatMul-free sits, then I'm going to do the cheesiest thing that I have ever done. And I'm going to zoom out a little bit in this VC pitch deck and show you where the MatMul-free model sits. That's kind of right where you want it to be. And then these guys are going to expand because they're in BrainFloat 16 format, while these are ternary. So really, even though they're parameter matched, your MatMul-free model is using ternary parameters, which relies on considerably less memory. And that's really where you want to be. In terms of benchmarks, short context, medium context, up to about 4K tokens, you do just as well. When you go to longer context, that's when state space models with these finite memory windows tend to break down a little bit. That's not to say they're useless, because a lot of folks are now using hybrid models where they might replace 80% of their model with state space models and lift up long context performance with just a little bit of transformer spice. These things can really work well together. That's all well and good. Go ahead. Yeah. Should there be a dimension for the quality of generation? As far as the benchmarking in the MatMul-free model goes, we are testing it on quite simplistic benchmarks like Arc Challenge, MMLU, and whatnot. And so those are really in basic reasoning type tasks. Now, if quality is kind of your more subjective measure of sycophancy and whatnot, those tend to not be very appropriate benchmarks for models like MatMul-free, where we've only gone past the pre-training phase and avoided any sort of SFT, any sort of RL. At that point, that's where you want to bring in perhaps more subjective measures as well. Yeah. So yeah, different benchmarks are relevant. Yeah. Yeah, state space models have come a really long way as long as it's not too long. Where this kind of craps itself, needle in a haystack, recall retrieval. Yeah. Any other questions at this point? Yeah.
So when you create models, you train most of them on some specific data and test it in something else.
Yeah. Yeah. Excellent. So, perhaps you're reaching state of the art as far as quote unquote efficient models are concerned. And to be fair, there's no real competition on neuromorphic hardware, right? But if we're able to extract more value out of these small scale systems, these neuromorphic systems, can't we draw upon these ideas to make large scale systems more efficient as well? Maybe the only limiter is, I don't know, the amount of money that an academic lab gets. Actually, thankfully, we got a significant amount of GPU resources from ByteDance and Contium that let us scale up to much larger data sets. And this is what I want to show you now. Actually, now we're going into night mode. This is the sexy part of the presentation. So I'm already wearing shorts, so can't take me anywhere good. So, all right, so a lot of progress on large language models up until now has really been driven by some sort of scaling, right? A couple of years before ChatGPT was a thing, people were paying attention to this. Jared Kaplan and his co-authors from OpenAI uploaded their preprint neural scaling laws for neural language models. Now, if I was to really simplify their findings, then I would just say that I told you this is the sexy part of the presentation. This is where the animations get fancy. I would just say that increasing the size of your models lets you get your test loss to go down, right? On some weird pseudo-log axis. But that loss only goes down provided that you also increase the number of training tokens. And this makes intuitive sense. The larger your models, the more data you need to take advantage of those parameters. Otherwise, you may not be using your compute in a very optimal manner. So what exactly does optimal even mean here? Let's say that you have a really good model, you're happy with it, but you want to scale it up. Now, the authors in this preprint found that an 8x increase in the model size should be accompanied with a 5x increase in dataset size, at least if you were to use your computation effectively. What that implies is that the size of your model matters more than the amount of data that you have. But that only applies for the specific conditions in their paper up to approximately a 1 billion parameter size. I think the language modeling community has diverged away from the conditions that were proposed in their paper and have honestly realized just how much data matters now. Nonetheless, that guided OpenAI and the broader LLM community to keep scaling the hell out of their model sizes, right? Now, if you increase your model size, you effectively increase the GPU hours that you need. It's kind of, if you increase your data set size as well, it's the same deal. You need more GPU hours. So if you have a particular test loss that you're chasing, you can kind of project the amount of compute that you need. And this dashed line along the kind of diagonal there, that indicates a point of compute optimality before your loss starts to saturate a little bit. So my question to you is, out of model size, data set size, and compute, what do you think is the limiting factor of these guys? Spoiler, dataset size, right? It's the problem with videos. If you think it's data, then excellent. We've effectively exhausted the internet. It is possible to generate high quality synthetic data, but really an upper bound on data means that more compute starts to become a little useless or just less useful. It deviates away from compute optimality. If you generate synthetic data, then there is no end to it. Checking the quality of that synthetic data can be a bit of a pain in the ass, but at the same time, there has been a good number of studies that have shown that, let's say that you have 10 trillion training tokens, you can augment that in a way to compress it down to 2 trillion and still get the same test losses that you care about. DeepSeek did it with OpenAI and breaching their T's and C's. But it is possible. It's just I guess it's a little bit more underexplored. It's not to say it's not worth going into, but it is absolutely underexplored at the moment. Yeah. So is there a way to decouple data from compute? Now, take a moment and think about that. You might have come across mixture of experts, which is a way to decouple parameter size from compute. But if you think of reasoning models, then you'd be on the right track here. There are a few ways to elicit reasoning. I can say think forever and just get my model to talk to itself for a little while. If you want to use the lingo, a chain of thought with long rollouts and self-checking, that might be the way. So say we ask our model a simple math question when we let it stream text in this rollout. Now, most humans would look at this, they'd have a mental lookup table for 6 times 4, and immediately you say 24, and that divided by 2 is 12. And this brings on the first problem with reasoning models, right? You're effectively forced to extend your context to run reasoning. The more context, the greater the risk of forgetting critical pieces of information. I'm sure many of us have had multi-turn conversations with LLMs and performance just degrades after several days. So while this math equation doesn't necessarily illustrate it, you can imagine that generating long blocks of code will bring on its own special challenges. If you've used Claude Code, it's got to quite regularly compress its context window. Now, as your questions get tougher, your model might need to undergo a few rollouts before it hits the right answer, right? Now, once it does hit that right answer, you reward your model, yeah? You might pick some of the incorrect answers and supply a penalty for those. You might not want to penalize everything, otherwise just too much imbalance. But what can you do to increase the chance of getting that correct answer? And take a moment to think about that. What can you do to increase the chances of getting that initial right answer? You can increase your model size and data set size, but then that's a bit of a catch-22, right? You've recoupled data and performance. That is to say that your reasoning still has an upper limit on that is set by the capability of your original base model before you fine-tuned it to be able to undergo reasoning. Now, if I take a data set of, say, 500 multi-choice questions, I pass it through my base model. It hasn't been optimized for reasoning. And I pass it in repeatedly up until 1,000 times. Now, my y-axis will show me the accuracy of my model. As long as at least one correct answer is given across the case samples, then we count that as a correct answer. We run this across a couple of models, the base model in blue or green and the RL rewarded model that has been optimized for reasoning in orange red. And you'll notice that given a certain number of attempts, it really does seem like the base model sets an upper limit, a ceiling on performance, right? So one school of thought, I think that this is just a school of thought, right? This isn't concrete. It's that reinforcement learning doesn't teach your model anything new, but rather amplifies pre-existing latent knowledge kind of hidden within your model, all the while trying to suppress incorrect answers. So the problem here is that the pre-trained model sets an upper limit on reasoning performance. Now, the third problem is that the model operates on your vocabulary. Why might that be a problem? Let me give you a fun example. So my parents are from Iran, and in Iranian culture, there is this ridiculously polite ritual of give and take. I might go to my auntie's house and she's going to offer me desserts. I'll say, no, I'm good. And she's going to offer me like 1,000 times. I'm going to say no every single time. And this kind of ritual of give and take, of this polite declining, is so ingrained into Iranian Persian culture that it has its own name. What is that name? I'm talking to you. Of course you knew. Tardoff. It's so prevalent that we know, right? It's Tardoff. There is no equivalent word for it in English. What that means is that reasoning in your vocabulary space cannot be the most optimal mode of reasoning. It makes more sense to do it in a latent space. Because, if you rely on predominantly English and Chinese tokens, which a lot of models are generally trained on for the most part, then different concepts will take a varying number of tokens to express, right? And to capture in a chain of thought rollout. And this sucks because the pre-training process is where you leverage trillions of tokens for training, and you're not really taking advantage of them for reasoning whatsoever. It's reasoning becomes a post hoc process. It's an afterthought to a pre-existing base model, right? And that's an artifact of or a problem of operating on a vocabulary space. So that leads me to the final model that I want to show you. And what we've discovered here is that merging reasoning with pre-training addresses all of these problems. It gives us a third axis of scaling that requires an alternative architecture, which we present in our recent preprint, scaling latent reasoning via looped language models. So let's first address what is a looped language model. So a standard transformer is going to take an input and generate an output after a bunch of layers. Right? Got this cute little data flow. In a looped transformer, we start the same way, but before generating the output token, the model is going to take the latent vector and pass it through this exit gate on the left, bottom left. And the exit gate asks, is this legit or should we try again? And if the exit gate is happy, denoted in green, then you terminate, you move on to the next token. But if the exit gate isn't happy and highlighted by red, then that latent vector is going to loop back around to the input of your model. And the process is repeated until the exit gate is happy to generate the next token. Keep in mind that looping isn't taking place on a word. It's not a it's not a token. It's really a latent representation, typically characterized by concepts. So you're no longer operating on the vocabulary. You don't need to generate a chain of thought, a chain of tokens, which helps compress your KV cache. And that means you don't need a pre-trained model to get this running, because this is optimized during pre-training. And suddenly you're able to take advantage of the trillions of pre-training tokens available to you. Yeah.
Display, and you just pass them as an input.
Yeah, exactly. Yeah, if you've come across universal transformers, same idea, just at a completely different scale. Yeah. So we dropped 4 models in total, Oro 1.4, 2.6 billion with thinking variants. Can anyone figure out why it's called Oro? Ouroboros? Hell yeah, nice. Yep, the infinity symbol. Yep. And when comparing them against state-of-the-art language models that are considerably larger, we are able to perform on par for the most part. And what you're looking at are the results of our 2.6 billion parameter model up against Qwen 3 and Gemma 3. It's worth noting that Gemma 3 12 billion is nearly 5x larger than Oro 2.6, and Qwen 3 is 3 times larger, but it's also trained on almost 3 times more tokens. These are reasonably simple short context benchmarks, and we've also got more challenging math coding benches in the preprint if you care about those fancier things and humanities last exam. Yeah. We unroll actually, we set a particular saturation of loops, and during training, we unroll the entire sequence length every single time. So we don't terminate early. There are very nuanced reasons as to why. I can go into more detail with you on that. It does mean that you have to manage your KV cache in a creative way, which I'm not going to bring up here, but we can go into detail. Yeah. So yeah, this is kind of the first time that we've seen looped language models pushed to truly industrial scales. There's this idea of dynamic termination as well, where simple tokens might exit early, and training on 7.7 trillion tokens is no straightforward task by any means, but there is still a considerable amount of internet left to keep pushing performance. But let me dig into a little bit more. Let's say that I unroll my looped model perhaps 2 times, right? I feed a sample of data into this 2-looped model. So it might be that the first exit gate is below some exiting threshold. So your latent vector keeps propagating. Again, this isn't a token. This is a latent vector. And on the second loop, the exit gate exceeds some arbitrary threshold that you might set as a hyperparameter, and then you terminate. If I want to push that even further, then maybe that's the case for a simple token that doesn't loop very much. But maybe this is a complex token. I want it to figure out supercalifragilistic, whatever. And then you have a more challenging word. And then the exit gate might take a little longer. The model wants to ruminate a little bit longer before terminating. So you have a more extended rollout to that point. Now, I will briefly show you the full training pipeline, and it's largely a very tedious engineering effort with the learning rate shown on the bottom. It's pretty standard LLM stuff, so I will point you to the paper for extra details, but to save a little bit on compute, the first pre-training phase involved optimizing the 1.4 billion model on 3 trillion tokens and then forking it into 2 separate pathways and just duplicating the non-embedding layers of the smaller model to get the 2.6 billion parameter model. And then, yeah, you relax the weights and keep training. So that kind of let us reuse a bunch of tokens on a smaller model. And then, yeah, eventually you do annealing, SFT, and then post-training to generate your thinking variance. The paper does also show the exact data distribution in the model using all open source data. In general, you want to increase the quality of data during your training phases, during pre-training to long context training to mid-training and whatnot. Those of you more familiar with continual learning can probably appreciate why you want the last thing that your model sees to be, high quality data. So that matters a lot, but don't need to look into that in too much detail. This leads me to the final set of results, and honestly, what I think are the coolest results in this entire paper, because a lot of this looped model is really empirical, right? I'm saying a bit more compute on compressed model results, good, right? There are a lot of low-level details that I am glossing over, but I think this is where we generate some actual insight. To make strong claims about when looping helps, then we really need total control over the tasks that our model is evaluated on, right? 2 tasks that might be worth testing include, can a looped language model memorize information effectively? And 2, can a looped language model understand and manipulate information more effectively? And so this is where the work on the physics of large language models by Meta comes in handy. I personally interpret these 2 questions as memorization versus, I suppose, understanding, right? That helps me make the distinction more clear, but it's more precise to refer to the first task as knowledge storage and extraction, and the second task as knowledge manipulation. They propose both of these things using highly controlled synthetic data sets. My description of these data sets will simplify the process a little bit, but it goes something like this. For storage and extraction, the data set consists of biographical information, the name, birthday, where they grew up, social security number, I don't know, just whatever that you might find relevant in a bio. The test is then asking the model to recall these facts. Spy Family fans in here, you know what's up. So it's simple Q&A, right? We tested a variety of models across multiple loops. So first, a 1 million parameter model using just 1 loop. That's that data point there. Then we cycled over 4 loops. So you see that little expansion. No improvement, didn't go up. We could try and increase the model size for a single loop. And that's what you see. And then test across 4 loops, but still there's no improvement going from 1 loop to 4 loops. Maybe we need to train on larger data sets. That's what you see now. And, we can go up to 50,000, 100K, 200K samples, but there's negligible variance between 1 loop and 4 loops in every single case. This holds true across all parameter scales that we tested and all dataset scales that we tested. What's the conclusion? Looping doesn't seem to help knowledge capacity whatsoever. That shouldn't be surprising though, because looping doesn't add parameters. Yeah, makes sense. How about knowledge manipulation? And this is where the model needs to go beyond pure retrieval and instead operate and reason on some of those stored facts. A few different operations are tested, but I don't know, here's one example where instead of asking when's Anya's birthday, it's, is her birth date even or odd? So you've got to operate on something that you can retrieve. Let's see how looping helps with knowledge manipulation. So on the x-axis, we have the number of training steps in 1000s. And on the y-axis, we have accuracy. One of the constraints is that no COT, no chain of thought is allowed. The model needs to immediately deliver the correct answer. And with 1 loop, see that the accuracy is going to saturate pretty damn quickly. It doesn't go beyond 14%, right? I'll show you 2 loops here. That shows a considerable improvement. And then when we go to 4 loops, even further. And so what this is showing us is that knowledge manipulation is where looping truly helps. That's where the benefit in all of those benchmarks came from. there's kind of looping provides extra opportunities for more internal computation, and that's what's going to give us a boost in performance. Using models of relatively smaller sizes compared to what the open source folk, Llama and whatnot, do. And I think this here is quite a powerful and insightful result. So there is a painful amount of detail in the paper. There is a YouTube video that goes with it, which recently released this called Neurodump, for people that struggle to read like myself. And I'll go into a considerable amount more detail on, I guess, learning rules and whatnot in the afternoon at 4 p.m., I think, for a biomedical focused neuromodulation presentation. So with that being said, none of this work is possible without the absolute stars in the lab. Most of this language modeling work came from Ridger over here with Taylor and Andrew on support for some of that work. And here's a long set of references from the looped language models to hybrid attention from our lab, MatMul-free in there as well, along with related work. Mamba's probably the most famous, but I do have to pinpoint Legendre memory units, which were the first by Chris Elias Smith's lab, which was the first to really introduce state space models and recurrence in the linearized parallelizable way, which kind of set the stage for everybody else to be productive with these types of models. So that being said, thank you for taking your Friday off.